So today we're going to talk about topic 10, lambda calculus. So just to recapitulate in the framework of what we've seen so far, where does lambda calculus fit? So remember again, we've seen the finite automata, and then we looked at PDAs and Turing machines, and also LBAs, or standing somewhere between Turing machines and PDA. Okay, that was on the Turing models of computation side. We looked at recursive functions, and we saw that recursive functions are equivalent to, in terms of computation, to a Turing machine. For recursive function, we do not have a strong hierarchy like we have for the automata. But we still have something a bit weaker than recursive function. If you remember, we studied the primitive recursive functions that are kind of part of the building block for the recursive functions. Recursive functions are the primitive recursive functions plus the mu recursion. Primitive recursive functions don't really correspond to LBA. They are somewhere because there are some primitive recursive functions that are not decidable. And if you remember, decidability, the bar of decidability, if we want, is somewhere here in between, right? So everything that is recognized, every language recognized by LBA is decidable, but not every Turing machine is decidable. It's kind of the same thing about primitive. So if we want to put like primitive recursive function, it would be somewhere here. Primitive recursive functions. So we don't have as much like hierarchy here on this side. And now we are looking at lambda calculus, which is equivalent also to Turing machine. So lambda is like the Greek letter lambda, so we can write it like that. And so we're gonna look at it. It's actually not that far from recursive function, but it takes another perspective than the function perspective. So lambda calculus can look a little bit overwhelming because of the notation is so new and different. I would like you to try to put that aside and think of it this way. A function, as you may have noticed, is not always very clearly defined. There are a lot of implicit assumptions on what is a function and what is a variable that we never actually clearly explicitly present. And so there is a lot of ambiguity around the notion of function. And you can see the lambda calculus as kind of a way to clarify things and really be very formal. It's kind of a formal version of functions. So here, in some sense, you have, I mean, they are all models of computations, right? They are all models of computation. But this model is clearly closer to the computing process. This model is much closer to the mathematical notion of function. And this, you could say, is kind of an in-between. Lambda calculus is using some aspect of computation, but also of the active computation, but also try to be formal like mathematics. What's the difference between function and computation? Well, a function, if you look at this function, right, f, which for x associates with x squared, right, which you can also write, f of x equals x squared, okay? And basically, the recursive functions work with functions like that, right? But they have this specific power of recursion, right? When you look at this function, well, what are you really saying? Are you talking about computation, about computing x squared? No, you're just saying like to each x, f is going to associate a the square of x, right? So a way to describe f, is to say that f is the set of all the ordered pairs of x squared, right? So f is going to be 0, 0. I mean, if you say that f goes from, say, natural numbers to natural numbers, right? Then I'm gonna have 0, 0, 1, 1, 2, 4, 3, 9, etc. Right? You can define f just as a set of pairs. If you look at that, you can say, oh yeah, I can see the pattern. The second number is always the square of the first one, but you don't have necessarily to know that, right? It could be something different, right? You could say, well, it's actually no, it's actually f of x equals x times x plus 0. Well, I can say, well, but this is the same, right? They are equal. Well, yeah, maybe from a pure function perspective, you look at that just as a set of numbers together. But from a computational perspective, no, that's not true, right? That's not true. If you have a square method in your program, computer program, you can just apply it to x. If you don't have a square method, you cannot do that. But you can do that. You can, if you have a multiplication method, you can multiply x by itself and add 0. The result will be the same, but the mechanism is different, right? A function is kind of static, defined as a infinite set with not this idea of computation. Lambda calculus is going to transform the function a little bit to add this notion of computation. And to make it clear, you could say, well, here is an example of a lambda term that is going to operate make this operation of squaring lambda x squared. So here I'm defining f. I'm going to put uppercase f to make the difference with the lowercase, and even though they are similar, but I'm going to define f as this, right? The abstraction from x of x squared. And then I'm going to say, well, I can apply f to x, and I get x squared. I can also apply f to y, and I get y squared. I can apply f to 2, and I get 2 squared, which is, by the way, 4. But you see that the way of thinking is a little bit different. Is f a set of predefined pairs of numbers? No, it's an abstraction. F is purely defined by that. It's not defined by all these numbers. Then you can apply it, and then you can reveal the response, but you don't have to pre-build it in some sense. Mathematics, in some sense, the traditional definition of function mathematics kind of assume that it's all like pre-computed. Lambda calculus, in some sense, doesn't assume that. It assumes that nothing is computed, and the point of lambda expressions is to express this computation. So f is truly, and you can think of it as an operator that is going to be to apply to an operand. And that's the way combinatory logic thinks about it, which is field very close. There are some allusion to it in the Fernandez book or in Dr. Blumenthal's notes to combinatory logic. But it's actually very close to lambda calculus. But it has this kind of terminology that is I find very helpful, even for lambda calculus, that we distinguish the operator from the operand. What is applied, what is applied to what we apply to. So f can be applied to x, to y, to 2. You can apply f to 0, and you can apply f to itself, right? That's also what is really interesting, is that you can get things like that. Or what does it mean? Well, it means the square of the square. Oh, okay, so the square of the square and this I can apply to, the number 2. So the square of 2 is going to be 16. Okay, so there is this kind of notion of applying and combining applications. Lambda calculus is just going to let us describe abstract functions like that. So you can see it has this kind of computational, really like pure computational aspect. F is kind of like a program, and 2 is an input, and I'm going to apply my program to my input to get a result. And actually, the equal here is not really correct. The equal here is not really correct. And we could say, well, that's correct. And actually, to be more precise, we usually use this to define rather than equality, because the equality means something else. But these are not actually really correct. The way we should describe them is as beta reduction. And that's the other interesting thing, is that we don't say that applying a lambda expression to a number equals another number. We say, no, it's not an equality. So I'm going to spell it out completely. Apply to 2. As such, this is not an equation that needs to be solved. It is what it is. We are saying that's what we call a regex, because we have a variable applied to another variable, and even though 2 can be a constant from a lambda calculus perspective, all of these are variables. So it's a variable, like m applied to n, right? And this can stand still. You do not need to solve that. It is just an expression in itself, right? But you can reduce that expression. And this is not the equality sign. And when I reduce it, I'm going to get 2 square. And in some sense, 2 square, I'm not going to go there because this is a bit out of topic, but in some sense, 2 square can also itself be reduced to get 4. Okay, but what is interesting to think about is that, well, why are we not using the equality? Because this is an operation. I have applied m to n, right? Or I have applied f to 2. So there is something that has been going on. So I have now operated the application. I can also undo it by going the other way, the other direction. But there is a before and an after. It is not a symmetric relation, right? In some sense, this is closer to what we call the normal form. That means the final form once all the regex have been reduced. The regexes have been reduced, have been beta reduced. That's the name of this operation. There is a direction, right? This is more reduced than this. This is a beta expansion of this. This is a beta reduction of this. There is a direction, just like a machine has a direction. A finite automata starts at a certain state, right? It starts at a certain state and it goes toward another state. Well, you can see the arrow, the transition arrow between two states, as kind of being an analogic to this, akin to this arrow here. So yes, lambda calculus is computational, in some sense more computational than recursive functions, because recursive functions are you could say static, right? That is important. That is important. It's not just purely philosophical consideration. That is important because that means, oh, I can consider f as a program that has not yet been executed. As, if you want, an automaton that has not yet received an input, and then I can give it an input, right? That's a very different way of thinking than functions, where f in itself doesn't have a definition without an x. You need a variable to define it. You need to say f of x equals x squared. F by itself is nothing, right? You cannot define f by itself. You need a variable to define it. In some sense, lambda calculus is abstracting from the variable and say, let's consider the function in itself as a program that can be applied to an operand, right? Okay, let's look just at another program, lambda expression that we can consider as a program. G is going to be lambda x, y, x plus y. And actually, I do not need the parentheses here because, as we'll see, the scope of after the dot of the lambda expression goes all the way to the right, except if you have parentheses. So we don't need them here. What is G? Well, G is also an operator that can be applied to an operand. And if you apply G to 1, and you beta reduce, what do you get? Well, you get 1 plus y, right? You didn't give it, actually, that's not true because we need to keep the lambda y, sorry about that, because this can be also expressed as, say, lambda x dot lambda y dot x plus y. So it would be, if you apply to 1, you're going to replace the x. And here I'm kind of moving ahead. We will go back. I'm just giving a bunch of examples so you can see where this is going and what's the point of this and why it's interesting. And then we'll look at the details. I've given only one of these. I didn't give two, right? If I said, well, J12, clearly J12, and that's why there are spaces all the time, because we don't want the ambiguity. If you look at the notes or the books, you can see sometimes spaces and you can find them strange. The point is to not have ambiguity here. G12 is 1 plus 2, right? And here I put a star because I've done a double beta reduction. So when I do a sequence of beta reduction all at one as a shortcut, I put a star to signify, well, it's not just one beta reduction, not just one step, but multiple steps, okay? Which can then itself be reduced to 3, right? If you do this kind of, if you add the notion of evaluation, which we won't talk about here. What is interesting here is that I can also just say G1, right? So G is an operator that can take two operands, but what if I take just one operand? What happens then? Well, I get lambda y 1 plus y. I get a new operator. You can call it G prime, or actually we should call it, we could call it G1. What does G1 means? G means add the two operators, or the two operands. G1 means add 1 to whatever you, okay? So G1, which can be, defined as G applied to 1, means add 1, right? And now I can, if now I apply G1 to the number 2, I can beta reduce to 1 plus 2. What is interesting here, again, is I'm able to have different layers of abstraction. I can say, well, I abstract from anything in the addition. And then I can say, well, I'm going to define addition with 1 and abstract only for the second term, or I'm going to define the whole thing, right? So there are a lot of combinations here, a lot of way to abstract, and I just wanted to mention that. Note that what I just did is really basically, in a sense, an example of what we call purification. And at some point in the course you have this. Purification consists in taking a function with several arguments, like the addition function, right? F of x, y equals x plus y, for instance, which is basically the g here, right? So let's call it g, be more consistent. And the lambda calculus allows us to actually operate a purification, which is I'm going to take always only one argument at a time. I'm always limiting myself to one argument at a time. So first, I'm going to take g of x, right? And it's going to give me a certain result. and then I'm going to do G2 of G1 of X. So this is basically what we did here, right? When I said, well, I'm first going to take 1 as an argument, it's going to define G1, and then G1 is going to be applied to 2. In this case here, if you notice, I have used only always with one argument. And this is interesting result because it shows that even for recursive functions, you can always redefine multiple functions of multiple variables as function of one variable. You can always redefine them so that they always take only one argument. Okay, so another interesting thing here I want you to notice, and that's the end of my introduction, is G1. I've been able here to define an abstract, both concrete and abstract, right, operator. G1 doesn't have a result, right? It's still an operator, it's still a function. I applied only one, and I kind of made abstraction, right? I can do G1, 2 to say, well, add 1 and 2. But I can also say, well, I'm going to suspend that. I'm going to wait. I'm just going to take G1, and that's going to become an operator. Then I can apply it to 2, right? So anyway, just wanted to emphasize that is that lambda calculus allows us to build kind of several layers of abstraction, and you can choose where to stop and say, well, I'm gonna take all the values, but I'm not gonna take this one. And this is very useful in many ways. You could make the parallel, and I'm not going to be too long on that, but you could make the parallel with natural language. Natural language, you can say, well, John likes Mary. Well, you can see that as a predicate with two arguments, right? Likes John Mary. Well, in everyday language, you can say, well, who does Jean likes? Well, when you ask the question, who does Jean likes? John, sorry. You kind of create another predicate, likes John, and you ask the question who, right? Well, likes John is really the application of, if you see it as lambda calculus, you create a predicate likes J that is the application of the abstract predicate likes applied to J. But you don't apply it yet to Mary. You don't know, right? So you just take this one and you define this and you ask the question, what does this new complex predicate, new abstract predicate apply to? Anyway, if it talks to you, great. If it doesn't, no problem. You don't need that, okay? So if it doesn't help, forget about it. Now, concretely, let's look a little bit more concretely at lambda calculus and the rules. I'm not going to go into the detail of, you have so many very clear explanation of the syntax and the rules and free variable and bound variable in the book. So for the syntax, it's pretty clear. What is well-formed lambda expression? I'm not going to go back to that. Free variable, bound variable. Let's talk just a tiny bit about that. If I say, again, and I'm using intentionally a lot of multiplication, addition, square. I know this is not necessarily in the book because they want to assume that we do not have these operations as given, but I'm using them as example because they can really help understand better the concepts. Now, after I've used them, we're going to have to forget about them and reconstruct them in pure lambda terms, right? Because plus doesn't exist, is not in the lambda calculus alphabet, right? It's not. So we have to do without it, right? But right now, I am going to still use it for the sake of example and understanding. So if I say lambda of x plus y, well, I have 1. It's going to help if I use some curves here. I have one linked variable. Sorry. That's Gallicism. Bound. And I have one free variable. Bound variable because x is bound through the lambda, which means that I do not need to specify, after this has been given to me, I do not need to more information on x. X is part of the definition of this lambda term. It's part of the abstraction. We say that x is going to be given as what this is applied to, right? So the same way that here, I did not need for this expression to be given x and y. I just need to apply this to terms, and that's going to fill in, the 1 is going to fill in the x, the 2 is going to fill in the y, as it is applied. Here is the same thing for x. For y, however, it's not in the lambda, it's not in the parameters, so that's what we call the parameters here and the body here. So y is not part of the parameters, so therefore, y is a free variable, which means that I need information on y. I cannot compute that. This is an incomplete. Actually, the one technical term we use sometimes is unsaturated, but not going to go there. It's basically an incomplete expression, right? If you say and you try to apply f, doesn't work. Doesn't mean that it's ill-formed. It is well-formed. It is okay. No problem. I'm just saying that if you apply it, I mean, no, you can apply it, but you will never reach a result as a natural number because you don't have the information on y. So let me correct that. You can apply it, right? Because f applied to 3, for instance, you're going to replace it by 3, you're going to get 3 plus y, right? Y in there is still a free variable, right? You do not have any bound through a lambda expression. And if you want to keep going and really compute the result, you're going to at some point have to give me y. Or if you don't want y to be a free variable anymore, you can also build on top of this abstraction an abstraction over y. You can define maybe g as lambda y of this expression, lambda x plus y. Now, y becomes now a bound variable, right? And I actually do not need these parentheses because, as we said, after the dot, the scope of the lambda after the dot is all the way to the right, everything to the right, unless you have parentheses that limit that. Right. Okay. So bound variable, free variable, it's fairly straightforward. It is important because when we come to alpha equivalence and substitution, it can be tricky. And actually, alpha equivalence, when you think about it, is very obvious. And in the Fernandez book, it's page 38. It's also explained in the notes. Basically, the idea is to say we need sometimes to do renaming, and this is because if I apply, say I apply this, g is applied to x. Well, if I apply g to x, I have a problem because my y here is going to become, so y is going to become here an x, and now I'm going to say, well, basically my expression jx is going to become 2x, right? X plus x, and that's not what I mean. This x here has nothing to do, is not bound here inside the expression, right? This x is not bound inside, it's outside, right? So so I might need to do some renaming. So I'm going to say that jx is the same as basically saying lambda y dot lambda z plus y applied to x, right? I'm applying this whole expression to x. And I just replace all the x's here by z, which is absolutely not a problem, right? It doesn't matter. Z is really truly only a placeholder. I mean, x is here only a placeholder, right? It's just to say, well, at this precise location, you're gonna replace the second term to be applied. First term is gonna be this one. So the number 1 after the parenthesis is gonna be here, right? And the number 2 here, right? So you're going to apply to, say, A, B. A is going to be number 1. B is going to be number 2. And all this is saying, really, the order here is just to say, well, you take the number 1 and you put it here. You take the number 2 and you put it here. That's all that this is saying. The fact that lambda y is first and lambda x is second. So really the x and y don't matter as letters, right? So you can replace them by z, that's the same thing. And if I replace by z here, the ambiguity of the x is disappeared, and I can now apply it for my beta reduction, and this is going to give me, so I'm apply, so x go here, right? The first one goes here, so it's going to be lambda z plus x. Now I have no problem, the x is not bound by this because I replaced by z, so I renamed it. So the renaming is really important here in this case, and this is where, just for the record, combinatory logic, because it gets rid of the variables, doesn't have to deal with that. So that's something interesting to look at. Here we still have issues with renaming and substitution. Okay, so so really that's important. The idea of the placeholder, that's really what Lambda abstraction is about. It's just to say where things are going to go. It's really a kind of idea of combination. So just to give the formal definition of the beta reduction, so if you have a reduction scheme, if you have a redex lambda x m applies to n, so to have a redex you need two variables, right? One applied to the other, and this is considered as, I mean, a lambda term applied to a variable, and you have m x replaced by n that represents the term obtained when you substitute x by n in m. Then you can say that this operation is the beta reduction. You transform, you apply, you beta reduce this redex by replacing all the x's in m by n, right? That's really what it means. Okay. Now, there are different reduction strategies, and we're going to talk a little bit about that. Just one thing for substitution in the lambda calculus. It's a special kind of replacement, right? When we say m, where all the x's are replaced by n, that means that we replace all the free occurrences of x by the term n, without capturing any free variables of n. And that's a very important notion, is that if you have any free variables of n, you don't want them to fall under the lambda expression in m, right? So here it's, again, when you look at it and you do it, it's more obvious than the theory. It's just that if somehow here, hidden in here, you have some kind of lambda z somewhere, right? Somewhere in M you have a lambda z, and somehow when you replace the x's in M by n, the n contains a free variable z. Inside. Well, the problem is that this z, you have to make sure that it doesn't fall under this lambda z, right? Make sure that we don't have capture, as we say, of this free variable. Because if this variable is free in n, it is supposed to stay free, right? So basically, what do? We just do a renaming. Let's call it S or T or U, V, doesn't matter, the name, but the name should not be the same if it's under the influence, I may say, of the lambda z. If it's not, that's not a problem. And it's not necessarily, it doesn't have to be. But if you have here just basically lambda z of x, right? If M is just lambda z of x, lambda z dot x, and you replace x by n, and n is basically z, well, you're going to get lambda z dot z, and that's not the meaning. That's not what was meant, right? Z was supposed to be a free variable, so it could be y, it could be anything. It doesn't have anything to do with z. It's just a coincidence that they have the same name. You don't want this coincidence to mean something different, right? So the intention of the naming is really given by which variable are under which lambda terms. Which lambda term, what is the scope of the lambda terms, and what are the variables in there. That's where the intention is, okay? So you need to just respect that and conserve that. That's basically the idea, and it seems fairly straightforward. This should not be a problem when you encounter this. But if you do a beta reduction in the topic 10 assignment, make sure that you are careful about that, and if some renaming needs to be done, do the renaming. Okay, so let's take an example just to illustrate that. Lambda x y of 2x plus y, right? Lambda xy is really lambda x dot lambda y, right? And I'm applying this to the variable y, okay? As a free variable, right? Doesn't have any value, it's just a free variable. You can think of it as being 1, 2, 3. Well, if I operate the beta reduction of this, I do not want y. Y here is not under the scope of lambda y. It's not, because of the parentheses here. So y is a free variable. Y could be z or s, u, it doesn't matter. If I just do the replacement, I say, oh, okay, so lambda x, I'm going to replace y by all the x's in this expression by y. I'm going to have lambda y. If I do something like without thinking of the implication of the scope of the lambda, I'm going to just get something like, oh, lambda y, 2y plus y. But that's not true. That's not correct. Because now my 2y, my x, is now under, this x is now linked by this y, which was not the case before. And this y is not supposed to be under the, there's no link between these two y's in some sense. They are just named the same by accident. The x here is not supposed to be under the y here, right? So lambda y 2y plus y is basically lambda y 3y. So this expression is basically saying, I'm going to multiply by 3 anything that is applied to. Anything that it is applied to. It's basically the notion of, this is triple, right? You can say, this define triple, right? Well, you're going to see it's completely different than the reality. The reality is not this. The reality is I rename that because there is potentially ambiguity. So in your program do that. I'm going to rename it Z, and now I'm doing my replacement. And there's no problem renaming it because y as a free variable equals z as a free variable. They are alpha equivalent. And now I can do my thing, and that's going to be lambda y 2z plus y. Oh, that doesn't mean triple. That doesn't mean triple. That means add 2z. That's the meaning. Add 2z to the number, right? Give me 2, I add 2z. You know, whatever z is, it's a free variable, so it's not defined yet. Okay, so triple and add to z have not the same meaning, so I have changed the meaning if I do not respect the renaming and I do not that properly. Okay, that's for the substitution. The normal form is the final version of a reduction, right? It's basically a lambda term that is not a regex. It cannot be reduced, beta reduced anymore, right? So, you know, if I keep going my example with plus, you know, L lambda x, lambda y, x plus y, I can beta reduce it, applied to 1 and then 4, I can apply it first time. It's going to be lambda y 1 plus y. Now apply to 4. I can apply it the second time. It's going to be 1 plus 4. And then I can compute it. It's 5, and then I'm done. Actually, here, technically, from a pure lambda perspective, I'm done here. There's no more reduction possible. At some point, you're done. You have computed. It's really the idea of, again, the computer program that has gone through, and you're over, right? At some point, your automata has computed the whole string. There's nothing else to compute, okay? That is the normal form. It's the arrival at basically an accept state or a reject state, if you want. So, that's very important, the notion of normal form. Some expressions are normalizable. That means they have a normal form. Some don't. Those who have a normal form have only one normal form. That's something very important. That if it has a normal form, it's going to be the same one. That doesn't mean there is only one path of reduction, but what we see is that in the path of reduction, even if you take different paths of reduction, at some point, the path will always converge. That's what we call convergent beta sequence of beta reductions, right? It will converge at some point. Even if it diverges at some point, some normalizations just diverge forever. These don't have a normal form anyway. They are not normalizable. And there are some examples that are interesting. You can look at them like lambda x xx, lambda xxx. You can call it the self-applicability of the self-applicability, applying to yourself. It's really a tricky one, but look at it. It's interesting to try to reduce that. You will never reach anything, any ending point. Okay, so that's something important. Now, strategies, the reduction strategies. So given that you can always find a normal form, you can ask, well, given that there is a normal form, you can ask, well, is there a technique to always reach the normal form systematically by reducing insertion? So yes, there is one. It's a leftmost outmost reduction. The leftmost outmost reduction always leads you to the normal form, but it's not necessarily the most efficient. It can actually be quite more expensive than other strategies like the leftmost innermost reduction. But I think it's interesting to notice that the leftmost outermost reduction always leads to the normal form, because that can be a really good strategy for your project. What does it mean leftmost outermost? It means that if a term has several redexes, we first reduce the one that is at the leftmost, outermost position in the term. That is the first redex starting from the left that is not contained in any other redex, right? That means, like, you know, if you have lambda x and then lambda y plus x, you're always going to start at the most, like, the most left and the most out of the nested abstraction. Because if you do the leftmost innermost, which is usually the most efficient computationally, but doesn't always lead you to the normal form, if you do the leftmost innermost, then you start with the most on the left, but the most also inside the nested parentheses, if you want, in the nested abstraction. So you start with this one. Okay, so that's basically it. I mean, then there is all these idea about recursion and booleans. I mean, just like we've done with recursive function, you can define natural numbers in terms of lambda functions. It's pretty abstract, but you should look at that. So you can define, 0, 1, 2, and we put a little hat on them because they are not specifically 0, 1, 2, but we can define them as lambda abstractions. For instance, 0 is going to be lambda x, lambda y, y. And 1 is going to be lambda x, lambda y, x, y. You could ask, well, that's not obvious that this is 0 and 1. Yes, it's just that in their behavior, the system we're creating here, it's going to work. It's going to work fine. And the notion of successor is going to depend on that. And you can also, same way, define the notion of true, false, not. You can even define the notion of conditional, like in a if-then statement in a program. So that's something really powerful that I invite you to look at. In the Fernandez book, it's page 47. It's really interesting. But this is like all building a system to basically show, oh, this is actually Turing complete. This has such computational power. You can compute this, this, this. You can also use that to show, as we do often, that there is at some point a paradox, and that you're going to find an expression that cannot be, in some sense, computed in the lambda calculus through by using diagonalization. So we won't go into that. This is something really interesting, and I might do a little like bonus video on that, but I don't want to confuse more with this. Of course, functional programming is highly based on this, right? So if you're familiar with Lisp or with Haskell, this should remind you of something. This is very powerful. Functional programming is really powerful in many areas. So I suggest you look at it. I'm talking really about purely functional programming, right? Where everything is a function. There is really something very powerful, partly for mathematical operation in this approach. Okay, so I'll finish here, and I hope this clarified a few things. And partly for the assignment, don't forget about the leftmost outmost reduction as a good strategy, and do not forget the notion of substitution with the renaming that is necessary so that a variable doesn't end up being captured by a lambda term. Okay, thank you very much.